Good afternoon, everyone, and welcome to this presentation. My name is Ramy Kheir. I am a PhD student in the Civil Engineering Department at Concordia University. Please let me start by introducing the topic of my presentation today, a validation study of the 4-peak point design method of a mobile crane rigging assembly with over 6 peak points. As we all know, mobile cranes are the centerpiece equipment in today's construction. This is because of their essential role in lifting, handling, and setting modules from their origins to their final destinations. These modules could weigh up to 160 tons and could take up to 16 peak points to lift. But what about rigging systems? A rigging system is the physical connection between the lifted module and the crane's hook. It is responsible for the load distribution while lifting. For a safe crane operation, modules should be lifted vertically and maintained in a level position during the lift, in order to avoid any rigging failures as well as module deformations. But despite the importance of rigging designs in terms of safety and efficiency, the existing methods were limited to up to 6 peak points only. To illustrate more the importance of rigging design, here is the data from the US given by OSHA for the fatal crane accident causes. We can easily notice that the highest percentage, 28%, is due to the failure of ropes and slings. On the other side, we see a 3D view of a rigging assembly. It is composed of a chain of elements. We have the slings, which are the diagonal and vertical elements, and they carry tensile forces. The spreader bars are the horizontal components, and they carry compression. Shackles and lifting points are connection points, and they carry tension also. The main objective of the study is to examine the static equilibrium method on a larger scale in rigging systems with more than 6 lifting points. This is done by extending the mathematical analysis in systems with 8, 10, 12, 14, and 16 peak points. The results will indicate the method feasibility in terms of analysis and design for each of the examined configurations, and also to open the way for a new design method that can be more efficient and accurate. The 4-peak point assembly consists of 3 levels. The calculation starts from bottom to top. So by considering the free body diagram of the module with the applied forces, which are the self-weight and the drop sling forces at the first level, and by assuming equilibrium, the summation of forces should be equal to 0. And the sling forces at the first level are computed. In a similar approach, the free body diagram of the spreader bar at the second level is considered, and by applying the equilibrium equations, the sling forces at the second level were calculated. Here are the equations of the 4 sling forces at the first and second levels. Now, by looking at the components at the third level, and by considering the free body diagram of the spreader bar with the applied forces, the static equilibrium method computed the 2 sling forces at the third level using these 2 equations. The existing method was also applied for a 6 peak point system, which consists of the 4 peak point segment plus a 2 peak point segment lying at the middle. The analysis of the 4 peak point segment was done exactly as before, while there was no analysis done for the 2 peak point segment. Its design was based on the selected components in the larger 4 peak point segment on a level-to-level basis, where both segments have the same number of levels. In the following slides, we will explore the 8, 10, 12, 14, and 16 peak point systems by applying the static equilibrium method. This is a 3D view of an 8 peak point assembly. To find the sling forces at the upper level, the free body diagram of the spreader bar is considered with the applied forces. Since all the other forces are knowns, a system of 2 equations with 2 unknowns is solved, and the sling forces at the upper level were computed using these 2 formulas. Now, by looking at the 10 peak point assembly consisting of both an 8 peak point and a 2 peak point segment at its middle, the same analysis can be applied for the 8 peak point. while for the two-peak point and following the same procedure as the existing method, there is a mismatch in the number of levels between the two segments, which jeopardize our design process. In the case of 12-peak point configuration, the solution was impossible, because when considering the free body diagram and by summing the forces to be equal to 0, we ended up with a system of two equations with 6 unknowns. In the case of the 14-peak point, the static equilibrium method is completely invalid for 3 reasons. The first is the uneven force distribution between the two segments. Second is that the analysis of the 12-peak point segment wasn't possible. And third is because of the mismatching number of levels between the two segments. And finally, we have the case of the 16-peak point system. It is the largest configuration consisting of 5 levels, where we need to compute the sling forces at the 5th level. So by considering the free body diagram of the spreader bar at the highest level and applying the static equilibrium equations in both directions, we were able to find the expressions for the left and right sling forces at level 5. To summarize the results of our study, we conclude that the static equilibrium is fully valid for the 8 and 16 peak point systems, partially valid for the 10 peak point system, and it's invalid in the case of 12 and 14 peak point systems. To conclude, we can say that the static equilibrium method works fine for small systems up to 6 lifting points. However, it becomes less efficient with more complex configurations. First, it becomes tedious for having to do a step-by-step systematic analysis for each level. Also, it's error-prone by having to use computed values many times for each new calculation. It also ignored other components and focused only on sling analysis. The uneven force distribution and the mismatching number of levels were two issues which encountered this method also. On the other hand, the method is still valid for configurations like the 8 and 16 peak point assemblies. It also provided a clear mathematical analysis and design procedure for larger rigging configurations. Finally, some recommendations. It will be useful to apply the finite element analysis for accurate modeling, for ensuring safe designs, and for performing a comprehensive structural analysis. Also, the study has revealed the necessity for a new design method capable of establishing equilibrium for large rigging assemblies using a simple structural analysis tool that can take into consideration dynamic effects, not only static loads. Thank you so much for listening.